I guess we're going to go ahead and get started. So it's a pleasure to welcome Dr. Adriana Gillman today as our colloquium speaker. She is currently an assistant professor at Rice University, and she is here to tell us today about fast direct solvers for boundary integral equations. So I want to thank you for inviting me and for all the people who made time to see me today. I really enjoyed meeting with you. It's been a very engaging day, and hopefully I can return the favor now. So I'm going to talk about one facet of my research, and that's fast direct solvers for boundary integral equations. I'll explain what exactly that means in a minute, but I'd like to acknowledge the people that contribute to the work you're going to see. So these are collaborators, and then these are my students. Yavin's work you'll see some of. Peter you won't, but I like having his name up there as well. I should be adding my postdoc. And then we're obligated to thank the sponsors, right? So they're there. All right. So this talk should be fairly accessible. So at any time you have a question, please feel free to stop me. I want to make sure that I don't lose anybody along the way. So I said fast direct solvers, and it may not be intuitive what do I mean by fast, right? Fast car. Well, what I'm talking about is fast linear algebra. So we want to compute or do numerical linear algebra faster than it would be if you used classic techniques. So we want a better asymptotic cost with a small constant. And the poster child for this is something that most people are familiar with, and that's computing the potential and locations caused by endpoint charges. This is a convolution. So you can do this via the FFT. And that will cost you n log n. If you do it the classic way, I calmed down about 5 minutes in. So just be patient. 5 to 10. Let me give myself a little buffer. So if you do it the classic way, convolution is a dense matrix vector multiply, right? So that's n squared. And then if you use an FFT, you can reduce that to n log n. And then if you use the fast multiple method, you get this down to linear cost. Now, the big key thing here, I'm not going to talk about what these guys mean. Most of you have probably seen the fast Fourier transform, but they are living up to the fast claim, right? They're asymptotically less expensive than doing it with dense linear algebra. So I'm not talking about matrix vector multiplies, I'm talking about direct solvers. So what do I mean by a direct solver? Well, if I'm going to actually compute, my goal is to solve a linear system like this, so AU equals B, I want to find U. If I do this for a dense matrix, it's going to cost me n cubed cost, where n is the number of unknowns. And so I don't want to do that, right? That's not efficient. So I'm not going to actually compute a direct solver. I'm going to compute a direct solver, an approximation to that solver. So I'm going to construct this operator T that approximates the inverse. And I want to do it in a way that I can have a fast matrix vector multiply. So I can apply it to right-hand sides efficiently. Is this okay? So that's my goal, is to compute fast direct solvers. So in this talk, we're going to focus on linear boundary value problems. This is going to be our poster child, the Laplace problem with Dirichlet boundary conditions. But you'll see other differential operators along the way. So you'll see some Stokes, and you'll see some Helmholtz applications. So we'll see that. There's two standard approaches to solving these types of boundary value problems. The first, and probably most popular, is to discretize the differential operator directly. So via finite element or finite difference. And then you end up with a large sparse system, but it tends to be ill-conditioned. You can build with preconditioners, or you can use, in some cases, multi-grid, and you do have direct methods for inverting that matrix. So these things exist. I do work on this area, but instead we're going to focus on this talk on this side, which is where you convert that boundary value problem to an integral equation. Then we discretize that integral equation via your favorite method. I'll show you a nice drum method, but you can use any other method. And you end up with a dense system whose size is determined by the number of points you're going to put on the boundary of the object. So here you fill points in space, here you put points on the boundary. And these boundary integral operators are written in a way so that you choose them in a way that you end up with a well-conditioned system. So no preconditioner, that's your goal. And then if you use the FMM to apply that operator, you can get a linear cost iterative method. And I want to build linear cost direct solvers for these systems. So we're going to focus on this one. So the difference between an iterative, this is maybe a review for most people in the room, but the difference between an iterative method and a direct method is that an iterative method is going to compute a sequence of approximations to the solution, and you hope that that sequence of approximations converges to the answer. Okay, I say hope. In some cases, you need to build the preconditioner to get that convergence, but it's pretty easy to get linear cost solvers in this situation. So the poster children for this, many of you have seen GMRes or conjugate gradient. Direct methods, you have Gaussian elimination or LU, and these are deterministic, so you know you're going to get an answer. There's no question of, is my answer going to be correct? But it's going to cost you a lot. So Gaussian elimination's incubed, but you have this robustness, and then once you've computed the inverse, solves are inexpensive. They're just matrix vector multiplies. So that's one of the nice features. If you're in a situation where you have lots of solves, it's nice to have the inverse hanging out. So when we create these direct solvers, we want them to be robust, great for multiple right-hand sides, and ideally have ON cost. Okay. All right. So we're back to our poster child. How do we actually end up with an integral equation from this boundary value problem? So we want to rewrite the problem so that it lives on the boundary of this object. And to do that, we're first going to look at a simpler problem, and that's simply the problem of solving a Poisson point charge problem. So that's the Laplacian, and then you have this point charge and at x naught. So this is x naught in space, and you can see that this is the solution. You can do a separation, and then you would just end up with this radially symmetric solution. And so you have a point charge. This is the solution to the point charge problem. This is okay? If you want to be able to move that point charge around in space, you get what I'm going to call the fundamental solution. And that allows me to move the point charges around in space. So I can put y anywhere I want. And this is really cool. So we're on our way to writing the problem and moving it to the boundary. So the problem with this guy is that he blows up at that point charge location. So I can't place a point charge on the boundary with this guy. So instead, I'm going to use what is called the double layer kernel, which is the normal derivative of the Green's function. And so this is a plot of him along a line, and you can see that it's smooth, and then there's a little jump here that is defined on that edge at that point. So I have a collection of point charges here. And so that is still a solution to this problem, right? Is this okay? Okay, so then how am I actually going to use this to solve the boundary value problem? Is that I'm going to write the solution as the convolution of that double layer kernel with an infinite number of point charges on the boundary. Right? So this is the integral of the double layer kernel with the boundary charge distribution. And so now it's an integral along here. And so we have that kernel. And so this satisfies the differential equation. And now we just need to force it to satisfy the boundary condition. And that's how we're going to determine the boundary charge distribution. So taking the limit as you go to the boundary, this is the 1/2. That's what you get from that jump at the interface. And so this is the integral equation we need to solve. Is this cool? Okay. All right. So we're not in the business of inverting integral operators. If this is a continuum, and I can't invert them. So we're finally at the point where we're going to discretize. So how am I going to discretize? I'm going to use a Nystrom method. And that's simply, I'm going to take this integral operator, and I'm going to apply a quadrature to it. So a quadrature comes with quadrature points and quadrature weights. And so this would be the discrete approximation of that integral operator. It's still not a linear system. So I say, hey, let's look for the solution at the quadrature points. And so this is one row equation of the integral equation. All right? Okay. So what we end up with is this linear system, A phi equals G, where A is the discretized integral operator. It's a dense matrix. That's kind of a boo, right? The size is determined by the number of discretization points, so the number of quadrature points we've placed on the boundary. And then it has the saving grace that it's data sparse or structured. All right. So now you're all like, what are you talking about, data sparse? Structured. What does that mean? Well, it means that the off-diagonal blocks are low rank. And that's something that we can exploit. So what do I mean by numerically low rank? Well, if I look at the singular value decomposition of an off-diagonal block, so this is the singular value decomposition of a general matrix. So U and V are the unitary matrices, and then sigma is the diagonal matrix with the singular values. And if you, it's low rank if I can choose an epsilon and find k singular values that are greater than epsilon. There's not many of them, right? So there's a small number of singular values that are greater than epsilon. All right, is that cool? Okay, so that's what I'm calling low rank, and a matrix that has this structure for the off-diagonal blocks is what we call a structured matrix. So let's make sure that I haven't lied to you. Great, that's a reasonable thing. So we're going to look at the off-diagonal blocks that correspond to the interaction of this part of the curve with the black part of the curve. So that this would be the block that we're looking at in the matrix. And if you look at it, this is a plot of it, so you see that it's nice and smooth away from the diagonal. It's a little bumpy closer. And that smoothness corresponds to this decay in the singular values. So the x-axis here is the number of the singular value, and the y-axis is the singular value in the log scale. So if I wanted to approximate this matrix to 9 digits, it would be a rank 29 matrix. Okay? So how do we take this and build a solver? Well, what we're going to do is we're going to block partition our matrix. So this is our matrix A, and we're going to block partition it here into 4 by 4 blocks. So the diagonal matrices we can't do anything with, we leave them. And then we have these off-diagonal blocks, and we're going to compute low-rank factorizations of them. But I'm not going to do each one individually, and I do this for a reason. I'm going to process this entire row, so that it's going to have the same column factor. So this UI is going to work for this entire row. It spans the entire column space, and then the VJ will span this entire column space. So, okay? So why is this nice? Well, I can take that factorization, expand it, and I end up with this factorization of the matrix, right? So this is all local, and then I can expand it out and factor out all those U's and those V's. And to really appreciate this, I think it's easier to look at the pictures, right? This matrix is now block diagonal, block diagonal, block diagonal. Only dense matrix is tiny, right? So we've actually, just in doing this one level of factorization, have reduced the cost of the matrix vector multiplier. And we have this nice sparse structure. So for our dense matrix. All right, so, okay, this is great, but you said you were talking about inversion, not matrix vector multiply. So how do we invert this? We're going to use the Woodbury formula. So this is the expression of the inverse. And the key thing to notice here is that we haven't lost that that sparsity pattern in the factors and doing the inverse. And our only dense matrix is this guy. And in computing him, we've only had, the biggest matrix we had to invert was that matrix itself. It's okay? All right. So have I given you a fast solver? No, sorry. But if you look at the factor, so that little dense matrix, because he comes from an integral operator, he actually has the same structure as the operator on the original system. So you can create a telescoping factorization. Oh, what if we could factor more? I forgot I had updated these slides. So yeah, that's exactly what we're going to do. We're going to factor this guy in a telescoping fashion and apply the Woodbury formula recursively. So this is the telescoping factorization of the matrix, and this is what the sparsity pattern of its factors look like. That's pretty cool. Okay, I think it's really cool. All right, so this is Q, but how do we, right, so now you have a linear inversion, but you need to compute the factorization. If you touch every entry in the matrix, all of this work was for nothing, right? That's n squared cost. So how do we create the factorization for O(n) cost? So this is where physics comes back into play. So fast factorization. So we're going to compute the factorization of the interaction of this with the rest of the geometry. So there's n tau points on there. And if you use dense linear algebra, then you're going to end up with n cubed actually cost for the factorization. Now you can be sneaky and say, hey, I know that the ranks are going to be low. And if you just use that and combine it with randomized linear algebra, you can reduce the cost to n squared. So now you're paying for touching every entry only. So the question is, how do we go from n squared to O(n)? And the answer is, we're going to exploit the smoothness of the kernel. So we know if you chop off here and here, right, all of this stuff looks approximately the same. So you could use a low order approximation, or not many basis functions to represent it, right? If you wanted to write down the function evaluating in the far field. Am I losing you? You're good. Okay. So the question is, well, how do we actually do this? Right? I don't want to actually go around finding the basis, so I'm going to use physics to choose my basis. And essentially what I'm going to do is I'm going to choose my basis to be a collection of point charges on an artificial geometry. So we call this a proxy surface. And so I've placed n proxy point charges there, and if I found the coefficients, Cj, I would be able to accurately represent the interaction between this and everybody outside of the geometry using. So this is a zoom in. So you can see him. So those point charges, we call them proxy points. And we don't actually need to compute these coefficients because we know that they exist. So instead, what we do is we just compute the interaction, the lowering factorization of the interaction of this part of the geometry, the part of the geometry that's near. So that's all of the black part of the geometry that's inside of this circle. And then these proxy points. So that corresponds to this matrix. And his size is n tau by n near plus n proxy. So you combine that with the randomized linear algebra, and you now have linear factorization.
So why did you introduce this extra geometry? I missed that, sorry.
I introduced it so I didn't have to touch the far field. So I know that I can, if I wanted to, I could write the far field interaction as a linear combination of these basis functions, where I would have to find the coefficients, and then I would be able to accurately find the interaction everywhere. So I would have to compute those coefficients to do that. So this is it's the same idea from the FMM. Okay, that doesn't help most people in the room on the old laptop. So for all the solvers, we pretty much partition everything into pre-computation, which is, I don't know what happened. Sorry, it's there. Don't fall. Okay, pre-computation is constructing the factorization and computing the inverse. And then, oh, but then it lost its, oh, no. He gets confused. Sorry, this is embarrassing. Okay. Is that better? Okay. All right, and then the time for a solve is the matrix vector multiply. All right, so we're going to consider 3 geometries. So you have a smooth star. We affectionately call this a star with corners. And then we have the snake geometry, and there we're going to increase the number of oscillations in the snake geometry with as we increase the number of discretization points. So here, everything, the separation between what parts of the geometry is about the same. Versus here, things are closer together. When points or space is close together, we expect the ranks to be higher.
The snake is finite thickness.
Yeah. Yeah, so it is a fixed thickness, and it has corners at the end. And it's just, we wanted to illustrate the difference that you can have a higher rank, but you still have linear complexity. And so here we have 3 plots of the top corresponds to the pre-computation. I need to move that over, sorry. So the y-axis here is the time in seconds. The x-axis is the number of discretization points. And so we have compression and inversion, and then this is the solve, the matrix vector multiply. For a smooth star, star with corners, and then the snake geometry. And you can see that the solver doesn't see the difference between corners or no corners. He just says, hey, ranks are low, I go. And then for the higher rank, you see the effect of the higher ranks in the shift in this line for the snake geometry. But what's really cool, so here it's what, 90 seconds to invert a 10 to the 5 matrix on my laptop, right? Y'all go home and do that. And then the matrix vector multiply is under 1/10 of a second, right? This is pretty sweet. So you're like, okay, fine, Adriana, this is cute, but this is not real life. One doesn't say scattering off of or solve full-class boundary value problems on starfish geometries. So we've been working on extensions, and one of the first extensions we worked on was doing far field scattering in 3D. And so yes, we still have the starfish, but don't worry, you will see a 3-dimensional object in a minute. So here, just so everybody's on the same page, the differential equation has changed, so it's no longer Laplace. We have this k, or this kappa, and that corresponds to the frequency. So you expect the solution to oscillate with respect to the frequency. We have a Dirichlet boundary value problem, and we say that the solution is radiative. And that just simply says that as you go out to infinity, the solution decays, right? So this boundary data is created by some object sending in incident waves. And then we are reading the data out at this geometry gamma out. All right, so then the slide starts to get a little overwhelmed. I did that on purpose so you can see. So this is creating the boundary data. G can be written in this integral operator. Then to evaluate the field, it's simply applying that double layer kernel to the boundary charge distribution that you would have found before. And so this T gamma inverse corresponds to inverting that integral operator. Okay? But we know that we're looking at far field computation, so gamma out is in and gamma out are far away, which means the matrices that correspond to Tn and T out are low rank. And this guy we know how to invert rapidly. You can do all sorts of fun business to create an efficient way of computing this low rank factorization of this operator that we call the scattering matrix. And I will save you how that actually happens, but I wanted to show you that it works. So this is scattering off of a trefoil, because that's realistic. And so we asked the solver for 9 digits of accuracy. The goal here is in 3D, memory's expensive, and direct solvers are too expensive if you just use them out of the box. So what we do is we create a low rank factorization with minimal memory cost by ditching what we don't need along the way. But this is fully exploiting the fact that we're looking at things far away. So this is the number of discretization points. This is the error and the approximation. And this is the time in seconds it took to build the solver. But what's important here is to get 10 digits of accuracy, I need 53,000 points on this geometry, but I only need to store a 900 by 900 matrix to evaluate the field for anybody outside. So I can send in waves wherever I want outside, retrieve them anywhere outside, and I'm simply doing a matrix vector multiply with a 900 by 900 matrix. This is not done on my laptop. This is done on a slightly glorified desktop computer with 120 gigs of RAM. And these are Fortran. We can handle slightly more complicated geometries. So this is a deformed cube. So it's a cube and went, right?
Curious, for the largest problem,
yeah.
What is the RAM required for that problem?
We don't report timings for the maxing out the RAM because you start to see cache. So it's probably around 100.
100 gig.
Yeah. And this is a parallel implementation, naively parallelized, but yeah. So here you have to do refinement out to the edges in order to get accuracy. So you need a lot more points, even though it's not very interesting geometry. So it's 86,000 points to get 9 digits of accuracy. But look, the matrix is actually smaller. It's because most of the points you need to resolve the geometry are not really useful at the end of the day for far field computations. All right, so this is cool. So I can do 3D, but this still doesn't seem super useful. So I've been working on a collection of additional, I call them accessories. I feel like that clock is not moving, or am I talking really fast? Okay. So the accessories, that's what the water's for, to slow me down. The accessories exploit the fact that there's a collection of problems that you can rewrite as low-rank updates to a boundary integral operator. And once you have a low-rank update, you can actually reuse the integral operator a lot. So again, I'm like keeping Sherman Morrison in business. You can write a matrix as a matrix plus a low-rank update, its inverse is given by this expression. So if this matrix is we call it HBS or HSS, has that structure that I can have the direct solver, then I get to have a fast direct solver for free, essentially, if I know how to compute this factorization rapidly. Because really, I don't care to construct the inverse. I care to construct the application of the inverse, right? So I can actually apply the Woodbury formula, and I have 1, 2 that are exactly the same, 1, 2 that are exactly the same, plus I can compute this inverse. This is going to be, as long as k is small, something I can invert really cheaply. If not, I can actually, sounds masochist, I can actually create an HBS solver for this guy. So we have not encountered a problem where I had to do that yet. Maybe in the future. So, okay, so is this cool? Low rank updates are cheap for solvers. So the question is, where do they arise in the wild? And the first place I saw them was for periodic problems. So my first problem was a periodic scattering problem, but it's easier to explain it for a periodic pipe. So assume that you have a periodic Laplace problem where, so this is your geometry is this pipe, goes on for infinity, just repeating. This is okay? Okay. And then your goal is, right, nobody wants to, the Green's function for that problem is an infinite sum. Right? I'm not in the business of computing infinite sums. Anybody else in the room? Okay, so nobody wants to compute an infinite sum. So what we do instead is replace that Green's function by a local or an element Green's function. So with the free space Green's function. So we say, okay, I care about the Green's problem on these 3 copies because they live inside of this circle. And then any geometries outside of this proxy, so I'm using the proxy surface again, I can capture the dynamics of that problem by understanding my interactions with this proxy surface. Was that clear? That was kind of jumbled. So I'm going to write the solution as a double layer kernel that lives on these 2 with an unknown boundary charge distribution plus the sum of a collection of basis functions where I have to compute the coefficients, right? So now my unknown has grown. I have the tau, which was that corresponds to the boundary charge distribution, plus coefficients, and that's here is an eta. I should probably update this so it matches the notation from before. Is that okay? Mm-hmm. All right. So this top row equation is the discretized boundary integral equation. Then this bottom equation is to enforce periodicity. So you know here that the solution is going to be the same at these 2 endpoints. Right? That's the definition of periodic for this problem. All right. So what is this matrix? A is the interaction of itself, so this unit geometry, plus the contributions from its neighbors, interactions with its neighbors. And those guys are far away, so it's a low rank matrix. Okay? All right. So then you can compute this inverse, and then once you can apply A rapidly, then you have this block solve, and it's super fast. All right, I'm losing you guys. Let's go to flashy pictures. So, so the first place I applied this was free space scattering problem. So here we have an infinite array of these geometries that we call the hairy amoeba. And so we're sending in waves. We want to be able to do a lot of them. People like to produce something what they call the Bragg's image. Physicists, you know what I'm talking about? Okay. So they want to solve it, they want to look at the solution for a collection of incident waves, essentially. And if you use the previously state-of-the-art technique, which was FMM plus GMRes, with our integral equation, it took 1 hour for one solve. This is expensive, right? Too much time. Even though you have a second kind integral equation, it's not helpful. So if you use the fast direct solver, it takes 4 minutes for the pre-computation and 15 minutes for the block solves for 200 right-hand sides. This is a 600 time speed up. Right? This is pretty cool. All right. Cool. Integral.
The problem now is an infinite row of these hairy amoebas.
Yes, infinite, forever and ever.
And then plane waves coming in at different angles of incidence?
Yes. Yes, that's the problem. So you have an infinite array of them, and then you want to send in lots of, and so, yeah, so this, and we can do it doubly periodic as well, but for this we just did quasi.
When you talk about the conventional rate, that means that you're using a periodic Green's function?
No, that's even slower.
Yeah, I know that was slow, but that's why I wanted to know.
No, so this is actually using a variant of the generalized periodizing scheme. So the original variant was a little different. It's now been generalized, but Yeah, so this is comparing apples and apples. So these are both using the same integral representation for the solution. These are comparing the same solver on the same, or different solvers for the same discretized problem. So you need 10 to the 5 unknowns to resolve this guy. And then right now, I think this is what's like the mid-frequency machine. So it's not even. Is this good? All right. So what's another problem where you have lots of solves and you may have periodicity? The Stokes flow. So here we have a periodic pipe. We have a collection of vesicles. So we're pretending these are red blood cells. I'm honest. So they're flowing through the pipe and then they come back out the other side, right? And so so we use a semi-implicit technique which decouples these two problems. So the problem for the vesicle gets decoupled from the walls and they act as forcing terms for each other. And the big thing here is that you have to do something special to handle the walls. So the wall problem is very easy if it doesn't know about the vessels. But in order to get accuracy for the vesicles, you need to discretize the walls in the same order or do something special for evaluation. And so we said was like, okay, let's just build a direct solver for the walls, the periodic walls, and maybe it's time for a movie. Let's see. This might be too much. Is that too small? So there's 1,000 vesicles flowing through this periodic pipe, and the spacing of the points on the wall is on the order of this. These have little trapezoidal roll on each of the vesicles, 32 points. And so for this problem before, the time stepping of the wall to compute one time step dominated the cost, solving the problem on the walls. But when you use the direct solver, it now takes 2% of the cost of a time step. So the cost of a time step completely got shifted, and now we need to come up with better ways of handling the vesicle wall interactions. Essentially, we need to build a better FMM. That's how we're doing that. If that's too small, these guys are a little bigger. I have some files that run this faster, but I seem to have misplaced them. This is kind of a boring problem though, right? They move much faster in this pipe. Yeah, all right. Is this good flow? All right, so where's another place where we see low rank updates to the linear system? This is it's for locally perturbed geometries. So okay, so that sounds kind of silly. So in this picture, I have this bean-shaped geometry, and that's my original geometry, gamma K plus gamma union gamma C. And then I'm adding this bump, gamma plus. And I'm removing this gamma C, gamma cut. All right, so this seems kind of silly. You're like, who cares, Adriana, about adding stuff to a beam? But it actually has applications in a variety of fields. So once we have 3D up and running, this is my poster child, I like it a lot. So you have a submarine, right? The government spends a lot of money designing acoustic absorbing material, and then they build the submarine, and then somebody decides to they build some new technology, and this requires a new antenna, right? Do you want to redevelop your acoustic absorbing material, remanufacture your? No, I mean, that's not practical, right? They don't do that. So what they do is they take the antenna and they numerically, they simulate what is the radar cross section when I put it on different places on the geometry. Well, you can pre-compute the solver for the antenna, and you can pre-compute the solver for the submarine, and then you just have to build these little low-rank factorizations, which you can do very easily, and you now have a fast direct solver for scattering off of a submarine with an antenna that you can put anywhere you want. So one of the other applications we were talking about doing this is the swimmers putting for the flagella, because each one of those would be a low rank update to the system. All right, so how does this actually work? Back to the bean, is you have your linear system, so this is the original geometry. So for my more illustrative example, the submarine, this is the submarine. This is the discretized antenna. And then this is the update to the system that you would have to recover the solution to the integral operator on the new geometry. So it's a little different than the other system. But if you look at the factors in that matrix, APK is the addition, the interaction of the addition with the rest of the geometry. Well, that's low rank. AKC, well, that's the interaction of the part you're keeping with the part you're cutting. That's low rank. And then the interaction of the original geometry with the new geometry, that's also low rank. And in fact, the factorizations for this and this, we get to reuse a lot of the information. And so here's what the low rank factorizations look like. And so this is really cool. So we've applied this to a couple of different problems. So this is the problem that my grad student affectionately calls the Pinocchio problem. Because what's happening here is we start with this box geometry, and we are increasing the number of discretization points on the geometry, but we're keeping the number of cut points constant. So in order to do that, this guy is becoming thinner and thinner. And so here are plots of the computational costs. So here's the increase in the number of discretization points on the original geometry. This is the time in seconds. And this is the pre-computation. So the red line is if you computed the solver from scratch. And the blue line is if you use the new solver. And we have a factor, if I remember correctly, 3 speed up in the pre-computation. And the cost of the solves is essentially the same. So you're not paying much of the solves, but you're getting a much faster solver. So here we can actually see the constants. So these are the timings. And so this is the ratio of them. So yeah, the new solver scales linearly, 3 times faster than building the solver from scratch. And so it would take 100 to 200 solves to be less expensive to build a new solver from scratch than it is to use the fast solver, the new solver. It's confusing. All right. So the other thing that we're interested in that it can be useful for is adaptive discretization techniques for boundary integral equations, right? To have a boundary integral and adaptive discretization technique before, you would have to invert the system to see, did I get the right answer? Or know a priori the behavior of your boundary charge distribution. You know about the kernel, but you need to know something about the boundary charge distribution. So, so this is something that we're currently working on is adaptive discretization techniques. So here we have our starfish geometry. That means to move. And then we're cutting out this little segment which consists of 3 Gaussian panels, and we're placing it with an unknown, a specified number of Gaussian panels. So again, these are the time for pre-computation. This is the time for the solve. This is the number of discretization points on the addition. So here, the cost is going to be dictated by how many points you're adding, and there's going to reach a point where it's not going to be as efficient as building a solver from scratch. And that crossovers here around like 50,000, it looks like. So, right, 1,000, 5,000. So this blue is the new solver. This is building a new solver from scratch. And you can see that as the number of points grows, the new solver just becomes more expensive. Right, this is because the ranks are, the density, you can replace this and get this to go down, but not there. All right, so I have given you an onslaught of fast direct solvers for boundary integral equations, but I hope you have some intuition of now how they they work and how they're constructed. And probably the thing that was more mystifying to people before was how do you actually compute linear factorization, a factorization with linear cost, and that's something that I hope I've illuminated. We've seen linear scaling for 1D. For higher dimensions, so for the surface solvers into the 3 halves, but the constant's really small. So actually, there do exist linear versions, but we haven't seen the threshold where they're better than this. They're great for problems with multiple right-hand sides. So we saw an example where there were 200 right-hand sides and it was 600 times faster than solving one. Or solving it using an iterative solver. And then there's all sorts of extensions. So I showed you the periodic boundary value problems and the locally perturbed boundary value problems. We're currently working on coupling those two so that if you're doing Stokes flow in a pipe and you have a vesicle that gets close to the wall, you actually only refine the wall in the area where the vesicle is close instead of refining the entire geometry. So that's something that's in progress. Also in progress is globally evolving geometry. So not where we just have, I showed you a very static, so the submarine was a very static problem. But if you're trying to build solvers for large so vesicle that, maybe not even a vesicle, some geometry that's changing with space, so shape optimization problems. We're building direct solvers for that. Composite materials, additional scattering problems, trying to get these things to be useful for general applications. So I know that was a lot, but I hope it was engaging, and I want to thank you again for your attention and for having me.